Okay. Let me begin once again by thanking Sergej and Subhro for the wonderful program and giving me a chance to present some work. The title of my talk is Higher Textures of Featureless Insulators. So this will be about certain aspects of phase diagrams and phases that are captured even when phases are trivial, non-trivial, instead of being non-trivial. Let me begin with a very simple prologue by commenting that phase diagrams are a central object of study in condensed matter. But while there's been enormous success in classifying phases, how they can be glued together to form phase diagrams is actually pretty poorly understood. So for example, there's a lot of interest in what phases can have a direct transition between them, when they can be continuous, things like that. In fact, more surprisingly, at least from my perspective, was the appearance of these abruptly terminating transitions, which appears in perhaps the most practically relevant phase diagram of water, but also exists in other things like the Ising model in magnetic field, Z to abelian Higgs theory, as we saw in Sneary's talk. So these mysteries are actually much harder to resolve than what we can do with just classifying phases of matter. So this is what my talk is going to be about, at least peripherally. So my proposal is the following, fairly straightforward. If you think of phase diagrams as some kind of a Lego puzzle where phases are the Lego pieces, and then you slot them together, it's important to understand the shape of each phase of matter. Right? So if you do understand them, maybe we can just figure out how they're glued together. Okay, but what does that even mean? Like what do we mean by a phase of matter? Okay, so there's this very unhelpful poster of this movie called The Shape of Water, just for entertainment, that has nothing to do with it. But how do we even start beginning to pose this question? We can use perhaps the most powerful tool we have in equilibrium physics. I've actually borrowed this picture from Vijay Shenoy's slides from over a decade ago when I was a student and listened to his talk. So a useful way to think about this is you start off at a particular point, for example, water at standard temperature pressure, and then think about, in theory, like adding all possible coupling constants. For example, like, I don't know, chemical potential, hopping amplitude, spin orbit coupling, Coulomb interactions, phonon coupling, all kinds of parameters you can think of, and follow the phase as long as it doesn't encounter any phase transitions. Right? So in this infinite dimensional coupling constant space, we get all parameters that correspond to the full phase. But this is obviously infinite dimensional. Life becomes a little easier if you think about what happens in the Wilsonian sense. So if we start coarse graining these parameters and induce a flow, the renormalization of group flow in the space of theories, then we can actually look for basins of attraction. This is a slightly more sophisticated way of defining what a phase is. If we consider each basin of attraction, as I try to represent here using a figure, each basin of attraction represents a distinct phase of matter, and we can ask all these fixed points, the basin of attraction, what shape does that form? What do I mean by shape? Obviously we can't tell very small details, but we can ask straightforward questions like, are there non-contractible loops? If we take a loop and then map it in the space of coupling constants, is it always possible to shrink it to a point? Or if I take a sphere and then wrap it around some set of points in parameter space within a single phase, is it always true that I can shrink the sphere without encountering some kind of a level close? So if you've been paying attention to the names of the breakfast you've had at ICTS over the last week, particularly if you're not a native resident of the country, we've been served two things. One is something called vada, which has a non-contractible loops, and the other one, which is idli, which is typically served together in restaurants, which does have contractible loops. So this has very trivial homotopy, and this one does not. So the question is, once we take all these basins and then just put them apart, they have some complicated shape. It's an infinite dimensional space. But is it morally like idlis or morally like vadas? In fact, the surprising thing is, for large classes of phases, the mathematical machinery that helped us classify various phases can also tell us about what shape they are. That will be the core content of my talk. And we easily understand that, in fact, there are no idlis, there are only vadas. There are only, each phase, even the most boring trivial phase of matter, has non-trivial homotopy. Okay. That's right. So as you pointed out, the space is infinite dimensional. The good question to ask is, what are codimensions? So are there loops which are one-dimensional, whose contraction is subtracted by codimension 1 surface or codimension 2 surface? So is it possible that by tuning a finite number of parameters we can always find a gap closing? Surprisingly, even though the full space is infinite dimensional, these gap closing points are finite codimensional. Yeah, so non-contractible loop is too strong. It's non-contractible finite dimensional spheres. So yeah, to push this logic further, to give a concrete example, this is a true statement. If you consider the space of spin chains in 1 dimension, there's always going to be a 4-parameter tuned gap closing point in its vicinity. You can always close a spectral gap by tuning precisely 4 parameters. So in other words, it has non-trivial pi 3. This is a surprising outcome of this investigation. I'm absolutely not talking about critical phases, just the most boring trivial insulator with product ground states, adiabatically. So that's what it means to not be able to close a loop. You try to close, you try to close, try to close. At a certain point, you realize that there's something stopping you from closing. That's a gap closing point. The obstructions to closing non-contractible loops are gap closing points, some finite locus of gap closing points. Maybe if I go ahead, things will become clearer because words are much poorly suited to describe this than pictures. Okay. So to just give a few examples, what do these non-trivial families which I'm describing, like non-contractible loops, non-contractible spheres look like? There are various known examples which can be identified as such. The first is in the space of quantum mechanical systems, there are non-contractible spheres, and this is a representative of this family is just Berry's spin in a magnetic field. So you try to contract the sphere, you have to put h to 0, and there's a level crossing. Precisely. So the one phase in spin polarized, as you point out, has non-contractible spheres. There are 3. So this Hamiltonian has 3 magnetic fields, Hx, Hy, and Hz. So if you consider a unit sphere spanned by Hx, Hy, and Hz, it's well known that it has a non-trivial Chern number. So that's a topological invariant that tells you that as a family, the 2-parameter family of states is non-contractible. And explicitly in this model, what happens at the origin of the sphere is there's a less level crossing. You exit the space of unique gap ground states. A slightly more complex example, which I'll be discussing more, is the Thouless pump. It's a 1-parameter family of ground states for a 1-dimensional system, and that also represents a non-contractible, as I'll argue. So in this talk, what I'll talk about is how these non-contractible loops and so on appear in real phase diagrams. Like what does it look like? I'll argue that there are geometric quantities we can calculate, that like the Berry phase and its higher generalizations that have been investigated. It actually brings out a topological texture in the phase diagram that makes all this very vivid. So this talk is based on recent results that should be out soon with Nick Jones from Oxford and Shashank Singham Reddy. Shashank's an undergrad student who's looking for a PhD position, super talented. So I'll be grateful if any of you have positions and are interested in it. Okay. So the talk is in 2 parts. The first one is, I'll spend most of the time. It's a warm-up system, something called the Rice-Millie model. It's a 1-dimensional system of spinless fermions. And then I'll just generalize this to arbitrary dimensions and present the general mathematical framework. Okay. So let me begin with a particular 1-dimensional model, which I'll focus on. It's a well-known model. It's called it's a model by Rice and Millie. So it's a model of spinless fermions with staggered hopping amplitudes. It goes as 1 plus delta and 1 minus delta on every even and odd bonds, and staggered chemical potential. Okay. So this is the model, and this has the second most boring phase diagram in the world. It has, if I tune the hopping amplitude from -1 to 1, and the staggered chemical potential from plus or minus infinity, it has exactly 1 phase of matter. And all of them are morally connected to some product state. So there's nothing topological about it whatsoever. Completely boring trivial phase. In fact, if you look at the symmetry class, I allow all perturbations. So if I look at the symmetry class, this belongs to class A. So indeed, if you look at the classification, it has only the trivial phase. But why I say this is the second most boring phase diagram as opposed to the most boring phase diagram is this point in between, just represented by an asterisk. It is obtained by setting both the staggered hopping amplitude and chemical potential to 0. When we have an ordinary tight binding model at half filling, so we have a gapless state. It's destabilized by either bond dimerization or staggered chemical potential. Now, why is this interesting? I'll demonstrate why the states are interesting in 3 different ways. The first, I'll go to the periphery of the phase diagram and then just look at what happens in form of a movie. So let's go to large positive chemical potentials. The chemical potential when because of the nature of this term, you only tend to occupy every odd sites. You have fermions on sites 1, 3, 5, and so on. Let's go all the way here. The site, let's track this fermions on site number 1. It now becomes delocalized on a dimer between sites 1 and 2. If you go to j goes to minus infinity, it's now it prefers occupancy on even sites. So this fermion which started on site 1 went between sites 1 and 2, now goes to site number 2. If I come here, it goes between sites 2 and 3. And when I come all the way back, the fermion finds up in site number 3. So as I go all the way around the periphery of the phase diagram, the charge is transported by precisely 1 unit cell, which is why it's called a charge, Thouless charge pump. Yeah, so that's the family of states at the periphery. I can't hear.
At Hamiltonian, how are you defining the infinity for J?
How am I defining infinity for J?
So J is the multiplicity of that second term, no? So how at the infinity is coming? I'm not able to understand.
It's a tuning parameter. So I tune it to infinity to see what happens.
Okay.
Okay, so this model can be analyzed in totality because it's a free fermion non-interacting system. So I can pass on to the band theory, and it's very easy to check that only at the origin the bands cross. Everywhere else the bands are well separated with the chemical potential exactly at 0. So everywhere apart from the origin we have a ordinary single filled band. It's not topological. There's a well-known way in which we diagnose a Thouless charge pump, which is consider any loop in the space diagram. Okay, there are multiple types of loops, one which can wrap the origin, one which does not have to. In any case, we can define a berry connection in the usual way. Now, I treat the momentum space, since we are in the single particle framework, I treat both momentum and parameters on equal footing. So I can define a connection on both momentum and parameter space. So I use this symbol psi to represent the collective coordinates representing both momentum and the parameters. So once we define this, we can take the berry connection and define the first Chern number. So the first Chern number is something that can be integrated over any 2-dimensional surface. And I can consider integrating over a torus formed by any of the loops. Just take any parametric loop and the momentum space. So in this 2 torus spanned by a loop and momentum, I can integrate the first Chern number. And then it's easy to check that if the circle wraps the origin, we have a non-trivial pump, and then the Chern number takes integer values, in this case 1. On the other hand, if we consider any contractible loop, right, the Chern number vanishes and we get 0. So the Chern number is quantized. So it's a quantized invariant that tells you whether there are non-contractible loops. So this puncture over here in the middle is representative of the non-contractible nature of the space of matter. All this is well known fairly, but we can do something better. We can just consider, instead of computing the Chern number at each point in parameter space, we can compute using the berry connection. We can just integrate the berry connection over just the momentum direction over the S1. The standard way of computing the berry phase. And if we consider the berry phase at each point and just plot it at for every parameter value, we notice something very familiar come about. So this of course, everybody would recognize is the topological texture of a vortex. And this generically is what happens when the system, the parameter space that we're considering has non-trivial topology. In fact, at this point, we can let go of all our assumptions we don't need translation invariance or free fermions. The Berry phase computed by integrating the Berry connection over the momentum direction, just over the Berry one for each point in parameters. Sorry, say it again. Yeah. One point in J and delta. I integrate over K. So I get a U1 well-defined angular variable for each point, and I can represent the angular variable using the angles of an arrowhead. Precisely. So as was pointed out, this can also be obtained experimentally, for example, by measuring the polarization, and one does not need any assumptions about the system being non-interacting, free, whatever. So this local observable actually points out how the phase diagram has a texture, kind of like surface of a cat or something. Yes. But it's not quantized. So Berry phase does not need to be quantized, and it's not. So it's not, I wouldn't call it a winding number. I'm not sure what you have in mind, but it's certainly not winding. That's churn number. You're describing the churn number. Oh, sorry, I think the expression for the Berry phase got erased. It's not many body, it's the single particle Berry phase. Yeah, it's a single particle invariant, but there is a polarization is the many body observer. Oh yes. I'm going to stay. All of this is well defined only in the gap phase when it's this one single field.
Here the plotting the that a Berry phase is like plotting a vector, right, in the delta and j direction. It's if you're
plotting an angle for each point in.
So if we plot a vector like in the I cap direction and j cap direction for any like electric field, we get a similar kind of structure.
I'm not plotting a vector. I'm just plotting an angle at each point.
Okay.
With using an arrowhead. So it's not a vector really, but.
But
it's kind of like what is this in an XY model? That's the closest analogy.
But Berry phase is vector in the K space, right? Vector potential in the K space.
No, we should talk later.
Okay.
Okay. So correct. That's right. So this is like a different way of looking at it. So let me move on to the second way of looking at the same thing, or the third way of looking at the same thing, which is we can just study the theory on open boundary conditions. So it turns out that when we study the theory on open boundary conditions, there's exactly one line where we have the system as edge modes. By edge modes, I mean zero energy edge modes, boundary zero modes. And it happens in a very particular way. It's a one-dimensional line in parameter space. It's actually a codimension one line, which terminates on this bulk gap closing point. And this is a particular feature which you cannot remove. So I claim that you can actually compute the whole thing is exactly solvable. So we can look at the correlation length of how well localized the edge mode, the boundary zero mode is, and there's an expression for it over here. So at the periphery, it's very well localized to the edge, but at the center, it delocalizes and becomes part of the bulk spectrum, bulk gap closing spectrum. And this is the manifestation of bulk boundary correspondence, if you will. Yes. So these broken lines are the locations where you see the zero energy boundary modes. In fact, a very careful observer would understand why this is happening immediately. If you tune J equal to 0, the staggered chemical potential, what you get is precisely the sushi for Higger model. So this actually seems like an accidental feature. Like, I tune J to 0, I have the sushi for Higger model. Sure, there are edge modes. In fact, it's not. So the anomaly that appears here is a special kind of anomaly. It goes by the name of anomaly in the space of coupling constants. And the easiest way, in my opinion, to demonstrate this is take the same model and add a finite chemical potential. So the effect of that is the gapless point blows up to form a gapless phase. There's a stable region where you have a gapless metallic phase, one-dimensional metallic phase. What happens to the edge modes is very curious. The red and the blue lines now represent edge modes on the left and the right end of the chain. So in this parameter regime, the system has edge modes only on one of the ends but not the other. Whereas on the blue line, the system has edge modes only on the right end. So this kind of a phenomenon does not happen for ordinary topological phases. So this boundary phenomenon is some kind of a global thing that occurs in phase diagrams due to the presence of non-contactable loops. It's not associated with any topological phase of matter. In fact, in the presence of chemical potential, there are no symmetry classes that have SPT phases, and none of these things are SPT phenomena. Okay? So we call these estranged edge modes because the name.
Could you explain again what happened over there?
Sorry, say again?
Can you explain again what happened over there?
So if you look at where the left edge modes lie.
I mean, what is the physical parameter change in your system so that from one point to this?
Oh, chemical potential. Ordinary chemical potential. I changed the filling number. That's it. So I start partially populating one of the bands.
Sorry, I miss, like, so do you think about it as some kind of SPT or not?
It's not. So this slide is meant to prove that it's not an SPT. Having edge modes on only one end but not the other doesn't happen for SPT.
Yeah, like not the ordinary one, but like there is some robustness still.
Yes, yes. So the robustness I claim is not coming from accidental SPTs, but the fact that I'm going around this in a non-contactable loop is a bulk boundary correspondence corresponding to that phenomenon.
So then what kind of phase of matter is it?
It's a trivial phase of matter in the usual sense, but it has non-trivial phase over a circle, if you like that kind of a terminology. I'm borrowing this from Hermely, but it just has non-contactable loops, is what I'm saying.
So it's not protected by symmetry?
It is protected by U1 conservation, nothing else.
It's protected.
By U1, just charge
U1.
conservation.
But it's not an SPT, although
not
it has edge modes.
That's
on
right.
This, like, on that line. Right?
That's right. SPT would require edge modes to be there for all parameters. So clearly it's not an SPT.
No, but imagine I just like fine tune to this line.
Right.
So should I think about it as I do not follow the logic. So that's kind of.
So along that line,
yeah,
you'll start as a person doing an experiment. You'll find the system without edge modes, phase transition at a critical point,
yeah,
and then state with edge modes.
yeah.
But the edge modes are on just one end.
You mean on this picture, right? When
No,
you
no.
go on.
So this picture represents the red line,
Yeah,
represents edge modes occurring only on the left end of the chain,
right.
physical left end of the chain. I might have my lefts and rights mixed, but only one of the ends of the chain. Just parameters, how the model, the details of the model. Sure, but the open boundary conditions change that because it's not symmetric because it's like, on one end there's like even occupancy, on the other end there's odd occupancy, so it breaks that symmetry.
Abhishodh, you had mentioned this, but forgotten. How important is the fact that the 0, point has translation of?
It's completely unimportant. We can see this, I mean, not straightforward, but using Bosenization, we can show that it's not important. For example, in the presence of interactions, you can break translation invariance. It's fine.
By this unit translation invariance?
Yeah, it can be broken.
Okay.
So, like I said, the translations are not important at all. The only symmetry that's important is U1. So the question is confusing because with periodic boundary conditions, there is no anomaly. The anomaly only occurs on the boundary. The system is not anomalous. The boundaries are anomalous. Like SPT phases, it's just the boundaries that are anomalous. That's right. So they construct effective theories for just the boundary, for example. That would be anomalous. So finally, usually for SPTs, you have edge modes on both edges. So this is, so the appearance of edge modes is connected to something called anomalies in the space of coupling constants. It's not an anomaly for the symmetries, like for SPTs. It's an anomaly between the symmetries. It's a mixed anomaly between the symmetries and the compactness of parameter space. I'm not. We can talk offline. Okay. So the whole thing can be understood very nicely using field theory. So the parameter for the system near the origin, we can consider an effective theory which is ordinary 1 plus 1 dimensional Dirac fermion, and the two coupling constants correspond to the two masses. If you remember Ashok's lectures, one of them is an ordinary mass and the other one is called a chiral mass. So it's precisely a conformal field theory with two relevant deformations. And so it makes sense that to close this gap, you need to tune to precisely two parameters. But what can be done is also we can reorganize the masses into something called the chiral form, the complex form, I'm sorry. Where it becomes very clear that under renormalization group, there are two constants. One is the radial direction, delta square plus j squared, and the angular direction, which is arctan of j over delta. Under renormalization group, both the mass terms have the exact same operator scaling dimensions. So only one of the parameters renormalizes. So m becomes very large, whereas the angular component does not renormalize. So in fact, it represents a moduli space of fixed points, which is precisely the shape of a circle, telling you that there are non-contactable circles in this space. We usually used to thinking about fixed points as points, but the correct way of thinking about it is like there's a manifold of fixed points which has some non-trivial topology, and that once again tell us the shape of the face of matter. And in fact, if we just plot alpha, which is what the theory renormalizes to, you once again get the same vortex at the origin analytically as you do by plotting the Berry face. Although we don't really have a connection between these two quantities, field theory and the Berry. Both. The fixed point is the basin of attraction. There's no point. It's a fixed. So the basin of attraction forms a fixed manifold. That's a circle. So the entire phase flows to one point on the circle. Each point in the phase flows to one point on the circle. Okay, so finally we can introduce interactions, and this was my interest. The gapless point actually under strong interaction splits up into a terminating first order transition, and we have a conjecture that all these terminating transitions can be interpreted as obstructions that appear in the middle of a non-contactable cycle such as charge pumps. Okay, so I'm very short on time, so I'll move on to I summarize and then move on to the final part of the talk. So there is non-trivial topology in the Rice-Millie phase diagram that can be detected geometrically using this vortex structure of polarization, and topologically we can compute the Chern number to any loop and momentum direction. And in field theory, we can just reproduce the same result by counting the number of relevant deformations obtained at the core. So I must say that the core of this vortex is called diabolical point by Kapustin and collaborators, and I'll use that terminology. Yeah, I would consider that as a feature, not a bug. So I mean, imagine what can happen for other phases. Yeah. More pragmatically, the same. Okay, a short answer is okay. Let me hold off on that question till the end. I have more to say about it. Okay, so how does it generalize? So for higher dimensions. So I'll begin by pointing out that the reason why all of these things are tractable is that Kitaev has a very interesting theory about the structure of the space of such states. So let me state a few definitions before stating Kitaev's conjecture. So ground states without topological order, like all the wonderful things that we heard in all the previous talks, I'll define them as invertible states. This includes, amongst other things, not just the trivial product state, but also things like quantum Hall, topological insulators, and so on and so forth. So these are called invertible states. So let me, if I have, consider the space of all invertible states in d dimensions with fixed attributes. For example, let's just say that bosons or fermions and whatever symmetric group that you want to consider. So with this fixed attribute, let me call such space as ID. Now, Kitaev conjectured about a little over a decade ago that as a sequence of topological spaces, ID, where D equals 1, 0, 1, 2, 3, and so on, these topological spaces form something called an omega spectrum. And this is determined by precisely one condition, which is if you consider the space in D dimensions, it has the same homotopy, like it has the same topology as the space of loops in D plus 1 dimension. That's what defines an omega spectrum. It's a series of topological spaces where with an index labeled by a number with 1, 2, 3, and so on, integer, such that the space in D dimensions is isomorphic, not isomorphic, is topologically equivalent to the space in D plus 1, the space of loops in D plus 1 dimensions. What is? Oh, no. So what does this tell me? This tells me the consequence of this particular phenomenon is that homotopy groups of the space in D dimensions related to a pi n of ID, what the nth homotopy group of the space of states in D dimensions, is exactly the same as the n plus 1th homotopy group for the higher dimensions. Exactly. So the important thing is pi 0 are nothing but the disconnected components, which are nothing but the phases of matter. So what this is telling you is that distinct phases of matter in D dimensions precisely label loops, non-conductive loops in D plus 1 dimensions. And this is completely clear when you look at charge pumps. Charges are the closest equivalent to a phase in 0 dimensions. And loops are labeled by charges, and hence they're called charge pumps. But more interestingly, you can have pump of charge pumps in 2 dimensions, so on and so forth. Now, okay, all this is nice, but how do we study this physically? So the expectation is that the vortex in 1 dimensions will guarantee that a generic phase diagram in 2 dimensions will have a topological structure of a hedgehog. Right? That's the 2-dimensional texture that one can expect. I should say 2 spatial dimensions. Parameter space has a topological structure of a hedgehog. So how do we see this? Now, this actually, so I should also mention that Kitaev conjectured this a long time ago, but recently there's this paper by Yosuke Kubota, who claims to have a proof of Kitaev's conjecture. For the small world of people who are interested in this, it's kind of a big deal. Anyway, so not only did Kitaev make this conjecture, but he also gave a recipe to construct, given a Hamiltonian family in D dimensions, there's a recipe which these authors have labeled the suspension construction based on some math result of how to construct higher dimensional models. And the result, in words is quite straightforward. You take D-dimensional systems and keep layering them in a particular way that introduces a new spatial dimension and introduce a new coupling constant to couple these, which introduces a new parameter. So new dimension by layering the lower dimensional system and new parameter that introduces the coupling between them. Of course, this has to be done in a particular way, but using this recipe, one can construct from lower dimensional family all kinds of higher dimensional examples. So we can do that precisely to the Rice-Millie model and construct non-trivial examples in higher dimensions, which are supposed to exhibit this texture. So in maths, this is what it looks like. So D-dimensional ascendant, as we call, of the Rice-Millie model can be constructed by layering these models with staggering for a particular reason, and then coupling in sort of a new dimer. This introduces a new parameter. So all of these continue to be free fermions, so we can analyze them completely without any excuse, and it can be pushed in a block form. So the block Hamiltonian has a very nice structure. It's a series of numbers coupled to gamma matrices in many dimensions. Of course, if you are familiar with the fact that K-theory is the thing that classifies free fermion systems, the appearance of gamma matrix should be absolutely not surprising, and indeed that's where it comes from. It's a subtle answer. You realize that to be in the right part of the phase diagram to see these textures, there is actually a minimal number of bands, as you'll see soon. If you keep increasing, it's fine. So there can be witness bands as K-theory would require, but if you make it too small, then you won't be able to see this. You'll just end up in a part of the phase diagram with nothing, no texture. Indeed, that's exactly why. Okay, so how does one, so I showed this vortex, so how do we get these vortices in higher dimensions? So as Apurva was asking, it turns out that for spatial dimensions D, this recipe produces a 2 to the D plus 1 band model, of which half of them are filled. So the number of filled bands are 2 to the D. So as we go in higher and higher dimensions, we get larger and larger number of bands. So for the model, the two-dimensional ascendant, we have 2 filled bands. Sorry, I think there was a typo. D is off by factor 1, so it should be D minus 1. So here you have 2 filled bands for 2 spatial dimensions and 3 parameters. So this is the phase diagram. There are 3 parameters which are labeled as delta x, delta x1, delta x2, and j. Since I just not describe them, but I'm happy to say what these things are later. But it's a free fermion model with 2 filled bands, and in this phase diagram, every point is gapped except at the origin. So to bring out the texture that I promised, what we need to do is take the 2 filled bands, and now we have multiple bands. So the appropriate thing to construct is a non-abelian Berry connection. So I construct a non-abelian Berry connection over, once again, the 2 momentum directions and the parameters. And if I enclose a sphere, I can now define the second Chern number, which is something that one needs to integrate over a 4-dimensional manifold. So the 2 coordinates of the sphere that I've wrapped over here and the 2 momentum direction will precisely give me the 4-dimensional space that I require. So to repeat what I said, construct for this 2-filled 2-band model the non-abelian Berry connection and the second Chern number, and evaluate it over the 4-dimensional manifold obtained by considering the sphere in parameters and the 2 momentum directions. Sorry, what? Corner. I'll come to the boundary soon. Let me just finish this and I will come to the boundary. So if you evaluate the second Chern number, it indeed evaluates to a non-trivial value, telling you that this represents a non-trivial sphere in the 2-dimensional model. But how do we get the geometric quantity, right? The equivalent of polarization. So it's actually quite simple. The polarization originally was related to the Chern number through Stokes' theorem, and one could do the same thing over here. So instead of evaluating for an entire sphere, we can evaluate some kind of a loop. We consider some kind of a loop and any bounding surface and evaluate the integral for the second Chern number. And what we get, as you would guess, is the Chern-Simons form. So this is a non-abelian Berry connection and the Chern-Simons 3 form, which if I integrate over any loop with the 2 momentum direction, will give me a good geometric quantity. And using this geometric quantity, one can actually find out, like, by foliating the system in a particular way, we can bring out this hedgehog texture. So what is this U1 quantity? Like, so this is a quantity that cannot be assigned to every point in parameter space, but for every loop in parameter space. So this is a manifestation of what recently has been studied and goes by the name of higher Berry phase. So I'll say more about that a bit later, but maybe for this. So typically for higher Berry phases, one usually needs to, there's a lot of work that's been done about these higher Berry phases. And for interacting systems, for example, spin chains, it has been known that, I'll finish in a minute. Oh yeah, I have 5 minutes. So it has been known that the appropriate quantity to consider are some very complex mathematical objects called gerbs. Indeed, like, if you look at these papers, they give you a nice way to go take a spin chain and then extract, discover this gerb structure. But it turns out that, and bundles such as what we're looking at are not good. But for non-interacting systems, it turns out that for all these gerbs thing that you consider, there's actually a very simple formula in terms of integrals of Chern-Simons forms that you can write down. And all of these things survive interactions. So if your system has some kind of a non-interacting free fermion limit, then you can extract all these interesting invariants from gerbs, this higher Berry phases and so on, but just by using free fermion models, by evaluating the Chern-Simons 3 form. That's one of our results. So we can generalize this to arbitrary dimensions. The topological invariant obtained by integrating over some higher dimensional sphere with appropriate momenta are some appropriate higher Chern numbers for some non-abelian Berry connections. On the other hand, if we want to consider the higher Berry phase for any arbitrary spatial dimension, it's the integral of some appropriate Chern-Simons form. And this, for example, for 1 + 1 dimensions, the second Chern number, the invariant you get is exactly what you get from something called the duaditic symmetry class for germs. The result matches, but the way to get it is much simpler. We can reproduce all of this using field theory. So the theory at the origin are two flavors of Dirac fermions. And we can do this process of computing the number of relevant deformations. So if you look at exactly our model, you get something called a triplet mass, which are 3. So it looks like this is fine. Like, you have to tune 3 parameters to close the gap. But then it's very well known that for 2 flavors of fermions, there's also something called a singlet mass. So it seems like I was expecting 3 relevant deformations, but I got 4. But for a technical reason, the singlet and triplet masses commute. They're actually not independent. So if you look at the independent masses, they're actually precisely 3. And if you add the singlet mass, something interesting happens, which is the gapless point at the origin blows up and you get a Chern insulator. It's just a thing that happens. Okay, so boundary, the edge modes. So for this model, edge modes continue to appear. They appear along this line in the space diagram. So you get edge modes by tuning 2 parameters. However, if you introduce a chemical potential, the gapless point at the origin blows up and you get a metallic phase once again. But curiously enough, instead of the edge modes separating like before, the edge modes actually become absolutely stable. So this is the point for 0 chemical potential, but for finite chemical potential, you get a metal. But the edge modes actually become more stable and you get this crown of edge modes that require absolutely no tuning. So if you are an experimentalist doing experiment at this point in the phase diagram, you'll find edge modes precisely of the form that you get in the quantum spin Hall effect. For example, the edge content is exactly the same. But this is completely in the trivial phase. And this is appearing from a different phenomenon. It's nothing to do with an SPT phase. It's appearing from the fact that somehow the system has non-contractible spheres. Okay, so that was the end of my talk. So yeah, phases of matter have non-trivial shapes. This explains the presence of terminating transitions, which is why I was interested. They can be exposed using topological textures by computing higher Berry phases. For free fermion systems, these higher Berry phases can be obtained as integrals of some appropriate Chern-Simons forms. And this produces some unusual forms of edge modes in all kinds of dimensions. So in higher dimensions, okay, so these are some outstanding questions that I would like to know the answers to. So in 1 dimension, I said that this is actually an experimentally measurable quantity, polarization. I'm not sure what the higher Berry phases correspond to, what measurable it corresponds to, what observable one can measure in lieu of doing this calculation on a piece of paper. Also, as was being asked, like this is really the most boring phase. We know of what non-contractible loops and so on look like in symmetry breaking phases, topologically ordered systems, and so on. So we know examples of this. What is missing is this Kita's magical recipe of how to guess the answer in every dimension using lower dimensional data. That is missing. We don't know what the equivalent of that is. But example by example, one knows, and there are many tricks like dualities and things like that, where we can take non-contractible loops and non-interacting models and then dualize this to get some interesting result for symmetry breaking, topologically ordered. So some of the things that we're looking at are, you can reinterpret like non-trivial topology of parameterized family of states. You can have various applications like interpret this as non-trivial topology of vacuum manifolds for symmetry breaking phases. That's one example. And if you introduce spatial inhomogeneities of a non-trivial topology, do you get something new? Turns out you do. Yeah, so with that, I'll end my talk, and if you have any questions, I'm happy. Circle, yeah. Indeed. I wouldn't call it the complex plane. Maybe you can, but yeah. It's the 2-dimensional plane of the 2 independent mass terms. Yeah, so the dimensions of the relevant parameters in higher dimensions is 3. You need if you look at an appropriate 3-dimensional space, you'll find. That sounds right. Yeah, thank you. I think that's about right. These are related to the higher 4D quantum Hall effect and 6D quantum Hall effect and so on. So the responses should be exactly what appears there.
Very elementary question. I have the impression in your constructions, the number of parameters have has to match the spatial dimension. Is it always the case? Or because it seems that the first example, you had a one-dimensional Brillouin zone, and psi was sort of a cyclic variable, and then
Just this example, but yeah, the observation is correct, but it's not necessary. For example, in one spatial dimensions, there's also non-contractible three spheres, which are not shown here.
so in your omega spectrum, you introduced this sequence of iterated loop spaces. D, should I regard it as the number of parameters or the
Spatial dimension.
spatial dimension? And the number of parameters is arbitrary, or?
So it's number of parameters is infinite in principle. This ID is like the space of infinite dimensional space of infinite coupling constants.
Uh-huh.
So it's telling you whether there exists non-trivial wrappings of spheres and things like that.
Okay. That's and this can be given a sort of solid mathematical formulation, because dealing with the topology of infinite dimensional manifold is by no means an easy exercise in mathematics, but you...
I don't have anything intelligent to say about that. The claim is that this works.
Okay.
By experience and so on, it works.
And when you're truncating to finite number of parameters, you can still, the claim is that you can still show the full topology of this infinite fold. Okay.
It is. It's the space of all possible invertible states. That's infinite dimension. You can map finite dimensional spheres onto infinite dimensional spaces. Yes. True. No, so if the space of Hamiltonians within a single phase is infinite dimensional, each of its ground states belongs to this space. Yes, that's one way. I must say, like, the formulation is not mine, but the exploiting of the results is mine. So I stuck to 3 dimensions in parameter space. It's not my mathematical achievement, so I would share their concern.
Any other questions? If not, we thank Abhishodh again. A wonderful talk.